So the other type of induction problem the syllabus would have us do, these divisibility problems. And so one I've got here, and when you think about it, logically it must be true. If I have 3 consecutive numbers and I multiply them together, the answer should be divisible by 3. Well, that makes sense, because every 3 you're going to get a factor that is divisible by 3 itself. That's not our proof though. We're going to induce the solution. This is a little bit different, because you'll notice I don't have a left-hand side and a right-hand side to work with. I've just got this statement, prove it's divisible by 3. So I can do the first step, prove it's true for n equals 1. So 1 times 2 times 3 is 6. Yes, 6 is divisible by 3. So good, that does work for n equals 1. So that's fine. But how do I write down my assumption? I want to assume for n equals k, where k is some positive integer, well, I do something like this. I'm going to say k times k plus 1 times k plus 2 must equal something that has a factor of 3 in it. So I'll simply write that as 3p. It must be equal to 3 times something. But that something has to be a whole number. Notice I didn't bother with z plus on that one, because it could be negative, that's fine. That would still be divisible by 3. So I'm saying, well, it's got to be times some whole number. So I'm saying p is some element of the integers. Must be a whole number. Okay. So what do I want to prove then? I want to prove k plus 1 times k plus 2 times k plus 3 is also 3 times something. This is the tricky bit. Oh, watch out, this is real tricky. Notice I didn't write p, I wrote q. Because logically, they're not going to be the same number. All right, here comes our proof. So we've got k plus 1, k plus 2, k plus 3. The question is, how do we get our assumption into that? Now our assumption, where are we, is that k plus 1, k plus 2 is 3p. So okay, I'm going to expand it out, but not completely. Because you'll notice my assumption had a factor of k plus 1, k plus 2. So I'm going to keep that as a factor. So if I expand that out, I'm going to get k lots of k plus 1, k plus 2, plus 3 lots of k plus 1, k plus 2. But there's my assumption, k plus 1, k plus 2. So I can say, well, hang on, that's 3p. That was my assumption. And look, we've now got a common factor of 3. So that's 3 outside of p plus k plus 1, k plus 2. The only thing we have to do is confirm that that is indeed a whole number. Well, p, we assumed that was a whole number. K, we assumed that was a whole number. If you add 1 to a whole number, you're still going to get a whole number. If you add 2, you're going to get a whole number. If you multiply 2 whole numbers together, you're going to get a whole number. If you add a whole number with a whole number, you're going to get a whole number. So yes, indeed, it is fair enough to say that that's equal to 3q, where my q is equal to p plus k plus 1, k plus 2, which is indeed a member of the integers. So voila, hence it is true, etc., etc., etc. Let's try another one. We're going to prove that 3 to the power of 3n plus 2 to the power of n plus 2 is always divisible by 5. So proof for n equals 1. I'll get 3 cubed plus 2 cubed, which is 35. Yes, 35 is divisible by 5. So that's good, works for the first case. So my assumption, all right, I will assume it's equal to 5 times some integer. So I want to prove that 3 to the power of 3k plus 3 plus 2 to the power of k plus 3 is 5 times, and I've called it q, some integer. How do I get my assumption into this one? This is where we have to be a little bit clever, and we actually rearrange the assumption. What I'm going to do is rewrite the first term there as 27, 3 cubed, times 3 to the power of 3k. 3 to the power of 3k, I'm going to say is 5p minus 2 to the power of k plus 2. Have a look at the assumption. That is the assumption. All I've done is I've moved the 2 to the power of k plus 2 to the other side. So I'm saying, hey, I could substitute in then for 3 to the power of 3k, 5p minus 2 to the power of k plus 2. Okay? Now, and this is a situation where I would definitely write down what I've done here, because it's not immediately obvious. I haven't just got my assumption and gone, bang, substitute here. So it's probably a good idea to explain, hang on a sec, what have you done here? Remember, it's a proof. You're trying to convince someone of your argument. Well, if I expand that out, I get 135p. Well, that's divisible by 5, so that's okay. 27 times 2 to the power of k plus 2. But then I've got also plus 2 lots of k plus 3. Well, I could rewrite my 2 to the power of k plus 3 as 2 times 2 to the power of k plus 2. And then I could add these two together. Negative 27 lots plus 2 lots would be negative 25 lots. And now it's divisible by 5. Because I can pull out a common factor of 5 and I'm left with 27p minus 5 times 2 to the power of k plus 2. And that would be an integer, because 2 to the power of an integer would be an integer. 5 times 2, an integer is an integer. And an integer minus an integer would be an integer. So yes, it is safe to say 27p minus 5 times 2 to the power of k plus 2 is an integer. So hence it's true for k plus 1 if it's true for k. And since we proved it for 1, then we can now induce that yes, it would be true for all integers. I could have done this same question, instead of substituting in for 3 to the power of 3k, I could have also, let's go back to the assumption here, I could have rewritten the assumption as 2 to the power of k plus 2 is 5p minus 3 to the power of 3k, and instead of breaking up the 3 to the power of 3k plus 3, I could have broken up the 2 lots of, what would it be? It would be 2 times 2 to the power of k plus 2, and then subbed in for the k plus 2. It doesn't matter, it should work either way. I'm going to go to one that's a little bit more tricky. We're going to play with polynomials now. We're going to prove that x to the power of 2n plus 1 plus a to the power of 2n plus 1 is divisible by x plus a for all integers. Okay, prove it's true for n equals 1. If n is 1, I get x cubed plus a cubed, and you'll remember our sum of two cubes would be x plus a outside of x squared minus a, x plus a squared. So yes, it has a factor of x plus a. So that is divisible by x plus a. Hence it's true for n equals 1. Assume the result is true for n equals k. All right. But this is where we've got to be careful here. We're not saying it's x plus a times an integer. We're saying it's x plus a times some other polynomial. So this time I'm saying qx is a polynomial. And so then I want to prove that x to the power of 2k plus 3 plus a to the power of 2k plus 3 would be x plus a times some polynomial. Okay, here's my proof. Same sort of idea. How do I get my assumption in? Well, I'm going to rewrite x to the power of 2k plus 3 as x squared times x to the 2k plus 1. And x to the 2k plus 1, I could rewrite as x plus a times qx minus a to the 2k plus 1. Expanding that out, x plus a, x squared qx, well that's got a factor of x plus a. What about these other two terms? There's a common factor there of a to the 2k plus 1, but look at what the other factor is. X squared minus a squared, which is difference of two squares. So it has a factor of x plus a, which means I could write it as x plus a times some polynomial, whatever that turned out to be. So yes, indeed, it is true where tx is some polynomial. And the rest is the same then, so hence the result's true for k plus 1, if it's true for k, and so on. So exercise 2b is the one on divisibility problems. Just a little note though. Imagine they just said prove it true for all integers, starting at 0 as the first case. So I can't just say n is an element of z plus. So this is how I would write it. For all n, an element of z, now the two dots, the colon, stands for such that. So n is an element of z such that n is greater than or equal to 0. That's what we're saying there. Now, if it was, say, for even ones, this is where it gets a little bit more involved, set notation. So if I wanted to say even integers greater than or equal to 0, I would say, well, for all n, there is an element of the integers such that n is greater than or equal to 0, there exists, so the backwards E stands for there exists an A, which is also an element of integers, such that n is 2A. In other words, an even number. This is where I would probably just use the words even integers. I probably wouldn't worry about set notation on this one. It's probably easier just to say, oh, well, prove true for even integers. Right? So,